So now that we've found our differential equations for the mole fraction, temperature of the water, and temperature of the gas phase, we can import them into Google Colaboratory and solve for these values via solving an initial value problem and converging the values using the root function. So the first thing that we need to do in order to do all of this is to import all of the tools that we're going to need. So the first thing I'm going to do is import NumPy, which is numerical Python, and this will allow us to run our code, and I'm going to abbreviate this as NP, just for simplicity. I'm going to import a tool called solve-IVP from a SciPy integration toolbox, so it should be from SciPy.optimize, or not optimize, integrate, we're going to import a tool called solve-IVP. Okay, and then SciPy also has an optimization toolbox, so we're going to import the root tool from the optimization toolbox so that we can converge the values of our initial value problem. So from SciPy.optimize, we're going to import root. And then after we have found the values across the different heights of the cooling towers for all three of our differential equations, we want to graph them. So in order to do this, I'm going to import the make subplots tool from plotly.subplots. From plotly.subplots, import make subplots. And then I'm also going to want to customize the background of our plots to have a dark background. So I first need to import plotly.io, which will allow us to change our theme. And I'm going to import that as io, as pio, and then pio.templates.default. We're going to set this equal to plotly dark. Plotly underscore dark, and this will give our subplots a dark background. So we should have everything imported that we need for this problem, and I spelled templates wrong, so we're going to fix that really quick. Okay. Perfect. So now that we have this, we're going to import all of the values we need to solve our problem. So we need to import all of the characteristics of water and air first. So we know that the heat transfer coefficient is 10, and this is in units of watts per meter squared Kelvin. And then after this, we need the ideal gas constant. So this is 8.314 joules per mole Kelvin, 8.314, and then joules per mole Kelvin. Just typing out all of the units as comments, just so we can keep track of everything and we don't miss a calculation because of our units. So the density of the air, so rho air, is equal to 1.2 kilograms per cubic meter. And then the heat capacities of everything. So the heat capacity of air is equal to 1,000 joules per kilogram Kelvin. Heat capacity of vapor is equal to, of water vapor is equal to 2,000 kilogram or joules per kilogram Kelvin. and then the heat capacity of liquid water. So heat capacity of liquid water is equal to 4,190 joules per kilogram Kelvin. And then we will also need to know lambda, which is the heat of vaporization. So heat of vaporization is equal to 40,700 joules per mole. Okay. And then after we have all this, we have all the information that we need to calculate the mass transfer coefficient Kc using the Lewis relation. So in order to do this, Kc is equal to the heat transfer coefficient above divided by the density of the air, so rho air times the heat capacity of the air, Cp air. So that should be good. And then we also want to import the values given in our problem statement over here. So we're doing a problem B2 of this exam. So we see that the height of the cooling tower is equal to 20 meters. And we can actually develop an array of different heights of the cooling tower. So I'm going to set it equal to a z value at every meter. So in order to do this, we can write a new variable. I'm going to call it z plot. It's equal to numpy.linspace, and then our parameters start, stop. So we're going to go 0 to 20. And then I'm going to say that we want 21 values because this will give us a value every meter up until 20. So we're going to use zplot is equal to numpy.linspace. And then after this, heat transfer coefficient is 10. The specific area is equal to 5 meters squared per cubic meter. And hot water enters the top at 70 Celsius. So temperature water in is equal to 70, and then I'm going to convert this to Kelvin, so 273 Kelvin. Okay, and then hot water enters the top with a flow rate of 0.5 kilograms per meter squared seconds. So the liquid flow rate is equal to 0.5, and that's in units of kilograms per meter squared seconds. And then air enters the bottom with a velocity of 5 meters per second. So 5 meters per second at a temperature air in is equal to 25 degrees Celsius, 25, and in Kelvin this is 273. Since everything is in Kelvin, it's just easier to convert. So this is in Kelvin, and it has a relative humidity of 50%, so equals 0.50. Okay. We now need to determine the vapor pressure of the water at any given temperature. So in order to do this, we're going to do the Antoine equation. So I have it pulled up here in Wikipedia, and the Antoine equation, the log base 10 of the pressure is equal to the A value minus the B value divided by the C value plus the temperature. And we're going to input this now. So I'm going to create going to define a function, and I'm going to call it vapor pressure, so VP, and the variable for this is temperature. So now I'm going to return the Antoine equation. So if we go down here, we see that we have it solved out for us. So the vapor pressure is equal to 10 to the power of the A value. So this is 8.07131, and then minus the B value. And for water, we have water between the temperature of 1 and 100 degrees Celsius, so we're going to use these values in the first row of this table. So the B value is 1730.63, and we're going to divide this by the temperature plus the C value. So we see that temperature in this is in Celsius, so we're going to say, since we have it defined in Kelvin, we're going to say the temperature minus 273 degrees, which will convert the temperature from Kelvin to Celsius. Temperature plus 273 plus the 233.426, and this would be that, and then we need to divide this whole thing by 760 millimeters of mercury, because we have this Antoine equation is in terms of millimeters of mercury, and we want this in pascals, so we're going to divide it by 760 and multiply it by 101.325, which will convert it to pascals. And actually, I forgot to put the pressure in this one, so I'm going to put pressure is equal to 101,325 pascals, and that will do that right there. Okay, so there's a syntax error. So it looks like there's a parenthesis error. So we have 10 to the parenthesis here. I think it's this parenthesis. Let's try that again. Maybe not. Oh. Okay, so we have 10 to the power of this parenthesis matches this parenthesis. These parentheses match. This one of these. Okay, that fixed it. So that will return the vapor pressure at any given temperature. And then we will move on from here. So now that we have created a function for the vapor pressure at any given temperature, we need to solve for the mole fraction of the air going in, and then also the gas flow rate of the air. So in order to do this, we're going to say that the mole fraction of the air going in, so YAN, is equal to the relative humidity times the vapor pressure at the temperature of the air going in, so tear in, and then that is multiplied by the velocity of the air. And then the gas flow rate of the air, the total gas flow rate is comprised of the gas flow rate of the air plus the gas flow rate of the water vapor. So the gas flow rate of the air is equal to the pressure, which is 101.325 pascals, times the molecular weight of the air, which I don't think I inputted up here, so I'm going to input the molecular weight of the air, which is 29 times 10 to the negative third, 29 e negative 3, and this is kilograms per mole. Kilograms per mole. And then the molecular weight of the water is equal to 18 times 10 to the negative third kilograms per mole. Okay, so the gas flow rate of the air is equal to the pressure times the molecular weight of the air, divided by the ideal gas constant times the temperature of the air going in, and then multiplied by the velocity as well. So now that we have that, we also need to make initial guesses for the outlet of the air and the outlet mole fraction of the air and the outlet temperature of the air. So I'm going to say that YA out guess is equal to the mole fraction of the air in, YA air in, and I'm going to add plus 0.1. I'll say add 0.1 to that. And then for the temperature of the air going out, I'm going to say, hold on just a sec. The temperature of the air going out, I'm going to add, or the temperature of the water going out. This should be temperature of the water going out. This is the guess of that. I'm going to add it to, so I'm going to say, where's temperature of the water going in? Oh no, this should be the temperature of the air going out. Sorry, my bad. This should be temperature air in, and I'm going to add, say, 6 to that for initial guess. Oh, I forgot to put a comment right there. This should be a lowercase p. Okay, so now that we have all of this inputted, we can begin solving the initial value problems. Okay, so now that we have defined all of the parameters and variables needed to solve for our differentials, we can begin to solve for them by coding out our initial value problem and converging those values. So I'm going to define a function called converge underscore y underscore t, and this function will converge the values of the mole fraction and the temperature of the gas so that they are lined up at the top of the column. So I'm going to say that, and the parameter for this function I'm just going to call v2. So we're going to say that the mole fraction of the water coming out of the column is equal to this parameter v2 at the 0 position in the array, and then the temperature of the gas coming out of the column is equal to the first position in this array. So now that we have this converge function, I'm going to create another function within this, and this function will solve the initial value problem. So I'm going to say that this function is called dyTwTg because it has the change in mole fraction, change in temperature of the water, and change in temperature of the gas. Those are our 3 differential equations, so that this naming makes sense. And then the parameters for this are z, which is the position in the column, and then v, which is just the independent variable value. Okay, so then I'm also going to define the mole fraction, the temperature of the water, and temperature of the gas, just so that we don't have to rewrite like v at 0, v at 1 every time that we want to type those when we're typing out our initial value problem, just so for simplicity. So we're going to say the mole fraction is equal to v at the 0 position. The temperature of the water is equal to v at the first position, and the temperature of the gas is equal to v at the second position. Okay, so in order to solve for our differentials, we have one parameter that we haven't really defined yet, and that's the gas flow rate of the water vapor. So we have the gas flow rate of the water vapor is equal to the mole fraction of the water divided by the mole fraction of the air, so 1 minus the water, since the mole fractions have to add up to 1. And then we're going to multiply this by the gas flow rate of the air times the molecular weight of the water divided by the molecular weight of the air. And this will give us our gas flow rate of the water. And then we also know that the total gas flow rate is equal to the gas flow rate of the air plus the gas flow rate of the water. And then finally, we only have the molecular weight and the heat capacity of the individual water vapor and the individual air. So we need to create a variable for the average molecular weight so that we can use those in our calculations. So the molecular weight of the average molecular weight is equal to the gas flow rate divided by the gas flow rate of the air divided by the molecular weight of the air plus the gas flow rate of the water divided by the molecular weight of the water. And then finally, the average heat capacity of the gas is equal to the heat capacity of the air times the gas flow rate of the air plus the heat capacity of the water vapor, so heat capacity of the vapor times the gas flow rate of the water, and then this is all divided by the gas flow rate of the air and water mixture. So now we can move to typing out our differentials. So we're just going to take these exactly from the equations that we derived in the previous portion of this exam. So I'm just going to copy these down really quick. So we first need to define the molar flux of the water, which we pulled out from two of our equations. So we can define this so we don't have to type it out every single time in terms of the variables. So this is the mass transfer coefficient Kc divided by the ideal gas constant divided by the temperature of the gas times the vapor pressure at the temperature of the water minus the mole fraction times the pressure. And then our first differential equation is the change in mole fraction with respect to position, and this is the negative specific surface area A times the average molecular weight divided by the total gas flow rate times the molar flux of the water that we just defined. And then the change in the temperature of the water is equal to the specific surface area divided by the liquid flow rate divided by the heat capacity of the liquid water times the heat transfer coefficient H times the difference in the temperature of the gas and the temperature of the water. So this will be the driving force of this differential, and then minus the heat of vaporization times the molar flux of the water. And then finally, we have the change in the temperature of the gas with respect to position, and this is the specific surface area times the heat transfer coefficient divided by the gas flow rate divided by the heat capacity of the gas times, again, the driving force of temperature, so the temperature of the gas minus the temperature of the water. Okay, and then after we have all of these typed out, we want to return all of these values. So we're going to return the change in mole fraction, change in temperature of the water, and the change in temperature of the gas. Okay. So after we return this, we need to be able to create a new field called sol, which will give us our solution of this initial value problem. So up above, we're going to define it outside of the main function so that we can access the values that we solve for outside of our converge function. So I'm going to say sol is equal to none, and then right above our function right here, we'll say that this is the global solution. So this will give us access to these values outside of this equation. And then I'm going to redefine sol within the converge function. I'm going to say sol is equal to solve underscore IVP. And the function that we're going to solve for is dytwtg. And then the time span is from 0 to the height of the column. So this will give us all the z values throughout the height of the column. And then our initial guesses. I'm going to say our initial guess for the mole fraction coming out of the column. So this is y out, which we defined in our converge function. And then I'm just going to say that our initial guess for the temperature of the water coming in is the initial guess for the temperature of the water going out. Since the heat capacity is so high, it won't make that much of a difference in the temperature of the water. And then finally, the temperature of the gas going out, which we also defined in our converge function. Okay, temperature of the gas going out. And then I'm going to define the method that we're going to use. So I'm just going to use the Radoux method of solving this. And we also need to say dense underscore output is equal to true. So this will give us our values all in the same thing. And then I want to define this solution at every value of the z plot that we created earlier. So if you can remember back, the z-plot was the linspace, so individual array values from the ground to the height of the column at 1 meter increments. So there are 21 values between 0 and 1, so this will be evaluated at all of these increments. And then we want to return the solution at the 0 position. And then we want to subtract the mole fraction of the air coming in. So this will give us the difference in the mole fraction of the air coming in and the difference between the air going out. So this will give us like how much the mole fraction has changed with time. And then for the second, we want to do the solution at 2, which is the temperature of the gas. And then we want to subtract the temperature of the air going in, and this will give us how much the temperature of the gas has changed throughout the entire column. So we're going to hit Shift Enter. Seemed to work, and then we are going to do our converge function, which will give us our values. So converge y underscore, we're going to do the root of our converge function. So root, our function converge underscore y underscore t, and then we need our initial guesses. So we're going to use the initial guesses for the mole fraction coming out and the temperature of the air going out that we did above. So we're going to do that here. So our initial guesses are y a out underscore gas and t air out underscore gas. Okay, here is the moment of truth. Converge, I spelled converge wrong. Converge, okay. Let's try it one more time. CG8, okay. Guess I typed an 8 in there somewhere. Where is that? Oh. This should be a times, not an 8. Oh, forgot to run that again. Okay. So it worked, we got our values, and now we can move on to graphing them. So I'm going to create a figure, and I'm going to set this equal to make underscore subplots, and I'm going to create a subplot with 3 rows and 1 column. Rows equal 3, cols equal 1. So this will, since we have 3 differential equations, we want to create a graph for each of them. So this will give us 3 different graphs kind of stacked on top of each other so that we can graph this. And then we're going to say fig dot add underscore scatter. And then we want to say that the x is equal to zplot. The y value is equal to the solution at 0, so this will be the mole fraction, and then we need a colon right here. So this will be the mole fraction throughout how the mole fraction is changing throughout time, so our solution to the initial value problem. And then we want to say that the name is equal to, I'm just going to call this the mole fraction of water, so mole fraction of water. And then we are going to say that the rho is equal to, rho is equal to 1, and then the column is equal to 1. So this will define it as the first graph. And then I'm actually going to copy and paste this so that, because the next will be the same, the x values will all be the same. So we're just going to change a couple of things in here. So this should be the solution at 1, and this will give us the temperature of the water, and then this will be row 2, column 1. So this will define the temperature of the water graph as the second graph. And then for the third one, solution at 2, and this will give us the temperature of the graph, or temperature of the gas, not the graph. Okay, so, I forgot to change this. So row is equal to 3, column equal 1. Okay, so here are our graphs, and they're a little bit spread out right now. So I'm going to say fig.update layout underscore layout, and I'm going to say the height is equal to, let's do like 500, and then the width is equal to, let's say, I want to do the height higher. I'm going to do the height is equal to 800, and then the width is equal to 500. Let's see how that works out. Okay, so that looks a lot better, and we can see that it gives how these values are changing with respect to time. I just zoomed in a lot. Okay, I don't know how to zoom back out. Zoom out, zoom out. Oh, maybe not. Okay, well, if you don't zoom in so much, it's not that bad. Okay, here we go. Anyways, so these are our graphs for the change in mole fraction, change in temperature of the water, and temperature of the gas. So that will be the end of exam 3. Thanks for watching.